are we discussing now? What was the last topic that we discussed? I into we found something, right? So force experienced by current carrying projector should not be carried. So how much is it? F is equal to I into L vector cross V vector. Correct? This is what we calculate. Now, this is F vector. So F was equal to I into L into V into sin theta, where theta is what? Where theta is the angle between L vector and V vector, etc. Right? So this is what we saw in the previous class. Right. Now, go to example 4.1 in your text. So go to example 4.1 in your text. So what does that question tell us? Read the data. Okay, a straight wire of mass. So there is a straight wire of mass 200 grams. Okay. And length 1.5 meter. So length of this conductor is 1.5 meter. Carries a current of 2 ampere. So carries a current of 2 ampere. Okay. It is suspended in the middle of that uniform horizontal magnet. So there is a uniform horizontal magnetic field B that is existing. If they give you the direction of current, what is the direction? Towards right here. So this is how the direction of current is. And there is a horizontal magnetic field that is existing. Correct? So there is a horizontal magnetic field existing from where to where? Is it into the plane or out of the plane? So if you observe, they would have given a table kind of structure and they would have told that this is the direction of magnetic. Correct? So the magnetic field is into the plane and the current is going in the rightward direction. So we know that F vector is equal to I into L vector cross V vector, correct? Now, using the right hand thumb rule, find out the direction of force experienced by this current carrying conductor. So using right hand thumb rule, find out the direction of force experienced by it. L vector is in which direction? This is in the direction of I cap cross. What is the direction of V vector? Minus K cap. So what is I cross K? I cross K is minus J. So minus of minus J will give you plus J cap. So this conductor experiences a magnetic force in the upward direction. Accepted? Now read the question again, you will understand things. So read the question from the beginning. What did they say? There is a magnetic. A straight wire of mass 200 grams. Okay, 1.5 meter carries current of suspended. Listen to this word. It is suspended in mid-air. What is the meaning of it? So what is the meaning of suspended in mid-air? Means if I have this marker, then if I remove my finger also, this marker should be able to stay in its own position. But how will that happen? Only if the forces are balanced. If I remove my hand now, what will happen? It is obviously going to fall. Why is it happening? Because of gravity. Whereas if there is a force, there is another force in addition to gravitational force that is existing, which can balance the gravitational force, then this will be able to get suspended in the middle. Okay. So we are very clear with the fact that the magnetic force is acting in the upward direction. So what should act in the downward direction to balance it? It's the weight of the object itself. Means actually it is like this. Visualize there is a table on which there is a conductor placed like this. Current is flowing in this direction. Okay, current is flowing in this direction, and the magnetic field is in this direction into the plane. So when you apply the right hand thumb rule, I into L vector cross B vector, magnetic force is in the upward direction and weight is in the downward direction. So they both are going to get balanced so that it is able to get suspended in the middle. Now, if I'm not wrong, they would have asked what should be the value of magnetic field for this kind of a scenario. Right? So it's very simple. What is the angle between L and B? 90. So magnetic force is equal to I into L into B of sine 90 degrees. Correct? I into L into B into sine 90 degrees. And the gravitational force is given as M into G. So these two forces are supposed to get balanced for this kind of a scenario to occur. So I into L into B into sine 90 is 1 is equal to mg, which implies B is equal to how much? Mg divided by I into L. What is M? 200 into 10 power minus 3 into G is 10 divided by I is 2 ampere into the length of the conductor is 3 by 2 meter. 2 and 2 will get cancelled. So 1, 2, 3, this 3 zeros and this is 1. So answer will be 2 by 3 is 0.67 Tesla. Correct? So it is 0.67 Tesla that is required for this situation. Sorry? It's bar. 0.6666 is PP count. Right? Am I clear with this? So with this, are we clear with how to apply this formula I into L into B along with the direction as well? Any doubt? Here?
Sir?
Clear of this? Yeah.
Sir, the diagram is glaring a bit.
Sorry, any doubt, guys?
Sir?
Those are online, any doubt?
Sir, the diagram is glaring, sir.
Okay. See, diagram it's from the textbook only. This one. So NP is in this direction, NG is in this direction. Okay. We draw it here. NP is like this, and NG is like this. Is it clear?
Okay, sir.
Yeah. Shall we proceed? The next one. Yeah. Now, so if you observe with respect to force, what are all the concepts that we have seen? Means a magnetic field will already exist, and in that magnetic field, if you project a charged particle, it starts experiencing force, right? Is that right? And similarly, if you place a current carrying conductor, that will also experience force. The next question is, what will happen if there are two parallel current carrying conductors? So if there are two parallel current carrying conductors, so write down the heading, two parallel current carrying conductors. Okay. If the situation is existing, let's say there is one conductor and there is another state current carrying conductor. Both are long conductors. So what do I mean by long conductors? Means they are of infinite length. Okay. And let's say they are carrying current I1 and I2 in the parallel directions. And the distance of separation between them, if I take it to be D. Now, what do you think will happen? If this kind of a scenario occurs, what will happen? Hmm? Any guess? So, one thing we are clear, so if you observe this whole chapter, there are 2 points that we observe. One is current carrying conductors generate magnetic field. Current carrying conductors generate magnetic field. And the second is current carrying conductor placed in magnetic field experiences are you accepting these two? Right, I repeat, current carrying conductors generate magnetic field and current carrying conductors can generate magnetic field. If you have a current carrying conductor which is placed in a magnetic field, it experiences force. Now, if you see the first conductor to be I, if you name the first conductor to be I, and the second conductor to be first conductor to be 1 and the second conductor obviously to be 2. So now the first conductor, will it not generate a magnetic field near the second conductor? If at all it generates, what will be the value of it? So I hope you have written this point. So what will be the magnetic field generated by the first current carrying conductor at point 2? Or I will call this point as P. Okay. Magnetic field at point P due to the first conductor is how much? Due to conductor 1 is how much? Mu naught I1 divided by 2 pi. Observe this diagram. 2 pi into d, correct? So if you take dp with a vector on top of it, that will be equal to mu naught I1 divided by 2 pi d in the direction of, give me the direction of magnetic field due to the first current. Apply right hand thumb rule. Current in the upward direction, so it will be into the plane. At this point, it is into the plane. So can I write it as minus k? Correct? So let me call this as 1. Now listen, this is the value of magnetic field produced due to the first conductor. So imagine there is a field present along the second conductor into which the second conductor is placed. Now, we know the facts. What is the second point I gave you? Current carrying conductor placed in external magnetic field will experience force. So what are the force experienced by the second conductor due to the field generated by the first conductor? So what is F21? What does F21 mean? Force experienced by the second conductor due to the field generated by the first conductor. Right? How much is it going to be? I. What is the value of I need to write? Current of the second conductor, that is I2 into, we don't have a proper length of this conductor because what did I tell you? It is a long wire. So I will take a portion of its length, which I will call it as L2 for the time being. Okay. Or I'll call it capital L. Okay. So can I write it as L into, what is the value of magnetic field at point P? It is mu naught I1 divided by 2 pi d, accepted. So I told you whenever I deal with vector, the first thing is I will always take care of scalar part, then I will be concerned about direction. So I wrote the scalar part, F21 is equal to I into L into B into what is the value of sin theta? Sin of magnetic field is into the plane, length of the conductor is in the plane, so angle is going to be sine of 90 degrees, correct? So this will be equal to u naught I1, I2 divided by 2 pi d into L. Right? This is the value of whom? This is the value of F21. This is value of F21. Now let's try to write it in terms of vector. Then how much will be the value here? Minus I cap. So how did you get minus I cap? Because L vector cross B vector. So L vector is in the direction of J cap and B vector is in the direction of minus K cap. So what is J cross minus K? J cap cross minus A. J cross K is I and you have a minus sign, so it becomes minus I cap. Is that clear? So here you can write it as minus I cap, and this is going to be the value of force experienced by the second current carrying conductor due to the magnetic field of the first conductor. So can I say that the second conductor will experience a force in this direction, F21? So it will experience a force in this direction. This direction I will mark F21. Okay. Now I'll give you 2 minutes time. Try to find out what is the force experienced by the first conductor due to the magnetic field of the second conductor. Try it out. Do exactly the reverse process. So what is the first step that you need to write? Find the magnetic field due to the second conductor at first conductor. So how much will that value be? B2. So how much? Or you can take this point as B dash. Find out what is BP dash. Anybody with the answer? What is BP dash? Mu naught I2 divided by 2 pi d. Because magnetic field due to the first conductor will involve the current from the first conductor. Magnetic field due to the second conductor will involve the current from the second conductor. So that will be mu naught I2 divided by 2 pi d. Write it down. So BP dash. Can I rub this portion first of all? Did you all copy it? Those who are online, did you all copy it? Copy this part?
1 minute, sir.
Yeah, please write it. Right? Okay. Akash, over. Did you copy it?
Yes, sir. Yes, sir.
Okay. Others?
Yes, sir.
What about others? Everyone has done?
Yes, sir.
Okay. So I'm rubbing this. So now what I'm going to do is the point P is going to get replaced with P dash. So it is due to the conductor 2. So how much is the value going to be? Mu naught I2 divided by 2 pi d. So if I write it in the vector form, what will be the direction? K cap minus K cap. Sure. Okay. So it is K cap because if you apply right hand thumb rule, then this side it is into the plane. So if one of the sides it is into the plane, on the other side it will be out of the plane. So it is K cap. So BP dash. What is the force experienced by the first conductor due to the current, due to the magnetic field from second conductor? So I1 into, I need to consider, I'll take the same length L. I'll tell you why I'm doing that. I'll take the same length L, okay, into, what should I write? B2 or BP dash, which is mu naught I2 divided by 2 pi into D. This is the scalar part. But if you have to convert it to a vector part, I need to put a bar on top of it. How much is going to be the answer? This right. So F12 vector will be equal to I1 into, or I write it like this. mu naught I1 I2 divided by 2 pi d times L. Can I write it like this, guys? Right? Now revisit the previous expression and tell me what was F21 vector. Mu naught I1 I2 divided by 2 pi d into L, but in the direction of minus I cap. Correct? Is it right? So if I observe the magnitude of both, what will I get? Mu naught I1 I2 divided by 2 pi d into L. Mu naught I1 I2 divided by 2 pi d into L. But since these two conductors that we have considered are long conductors, we will not be able to calculate the direct value of force. Rather, we'll be able to calculate only force per unit length. Means I need to bring this L, which I assume to be L, to the left hand side so that I'm able to get the expression only in terms of I1, I2, and the distance of separation. Because that is what we considered at the beginning. I1 and I2 were considered, and D is taken as the distance of separation. Correct? So are you able to understand this point? So from here, I can write F12 divided by L is equal to, I'm taking only magnitude, mu naught I1 I2 divided by 2 pi d, and F21 divided by L is equal to mu naught I1 I2 divided by 2 pi d. So if you observe, both the conductors will experience the same force per unit length. Is it not the case? So they will be experiencing the same force per unit length. Means in terms of magnitude, F12 and F21 are the same. Okay. So based on this only, they will be asking you problems. So one thing they'll ask you to derive is, if at all it is asked for a 5 mark. Okay. Generally, the 5 mark questions are like this: either 3-1-1 or 3-2. So 3 mark question followed by 1 mark and another 1 mark, or 3 marks followed by a direct 2 marks. So they can ask you to derive this and a problem based. Okay. So I hope the derivation is clear. Right. Now the next question is this. If these are the values, now I need to be concerned about the direction as well. So if I look at the direction, in this scenario, if you look at the heading, what did I tell you? I told it is a scenario where you have two parallel current carrying conductors, but I never mentioned what is the direction in both the conductors. So in this scenario, I considered the direction of current to be in the same direction. And I have taken the same direction. So suppose you reverse and take the scenario. If both the currents are flowing in the downward direction, maybe this would have become minus I cap, this would have become plus I cap. Not maybe, for sure it will happen. Minus I cap and plus I cap. Okay. So in both the scenarios, whether you take the current in both the conductors to be upward or downward, one thing I'm able to observe is the force is of course in the opposite directions. Except, but look at the way they are aligned. Means if the currents are in like direction, this will use again. Generally, what happens to like charges? Ripple. So if the current is in the like direction, they don't repel, they attract. In this scenario, that is what is happening. See, the second conductor is moving in this direction, and the first conductor is moving in this direction. So they get attracted. So currents flowing in the same direction for two parallel current carrying conductors will always create a scenario of attraction. Whereas if the currents are flowing in opposite direction, then they will repel. If you want, you can try and see. And what will happen is, if you take one current to be upward and the other current to be downward, this will start experiencing force to the right, and this will start experiencing a force to the left. Means this will move away and this will also move away, so they are moving away from each other. Moving away means repelling each other. Okay, so in this scenario, there is a slightly different condition. So what is the point? You should not think in terms of charges, you should think in this scenario. So unlike the case of like charges, here what happens? The opposite happens. Like charges repel, whereas currents in the like direction attract. So this is applicable only for the straight current carrying conductor. Please make a note. Any other doubt? And one more point is what? For these kind of scenarios, you can never calculate force, but rather what are you calculating? You can only calculate force per unit. Okay. Okay. So shall we try out a problem based on this concept? Open your textbook. Check if there is any problem given under this. Go to page 156, example 4.10. Page 156, example 4.10. So what is the question? Come and read it. What is the question?
The horizontal component of the Earth's magnetic field at a certain place is 10 to the power minus 5 Tesla.
Okay. 4.10. So the horizontal magnetic field.
Of the Earth's magnetic field at a certain place is 10 to the power minus 5 Tesla.
So B with the H at the bottom means horizontal magnetic field. What is it? You learn about this in the next step. Okay. So the horizontal component of Earth's magnetic field is 3 into 10 power
Minus 5 Tesla.
Okay.
And the direction of the field is from geographic south to geographic north.
Okay. So it is in this direction. So this is the horizontal component of Earth's magnetic field. Okay.
A very long straight current carrying conductor is carrying a steady current of 1 ampere.
So current is 1 ampere. Okay.
What is the force per unit length or if when it is placed on a horizontal table and the direction of the current is A east to west, east south?
So there are two scenarios, right? Okay. In the first case, when the current is flowing from
East.
so when the current is flowing from east to west, they ask you what is the value of.
Force per unit.
So if you observe this scenario, you cannot calculate force directly. Why? Because you don't know the length of the current. So F is equal to I into L vector cross B vector or ILB sin theta. Here theta is going to be how much? 0. So if theta in this case is 90. Yeah. So it is ILB sine of 90 degrees. So if I bring the L to the other side, L by L will be equal to I is 1 ampere into the horizontal component of Earth's magnetic field is 3 into 10 power minus 5 Tesla, and the answer is going to be 3 into 10 power minus 5 Newton per meter. Because it is force per unit. So in the second scenario, you can obviously solve it on your own. Okay. So in the second scenario, what is the answer? For B, obviously the answer will be 0. You will not experience force because the current and the magnetic field are in the same direction. Right? So you go to exercise problems. So you go to exercise problems at page 169. So in page 169, if you see, let's try out problem number 4.5 and 4.7. So try 4.5 and 4.7. Page number 169. Four point five is what it is. What is the question?
What is the magnitude of magnetic force per unit length on a wire carrying a current of 8 ampere and making an angle of 30 degrees with the direction of uniform magnetic field of 0.15 s?
You can solve it easily. So F is equal to B into I into L sin to sin theta. B is how much? 0.15 into L is not known. Current is 8 ampere into sin 30 degrees. This is the force. Bring L to the left hand side. F by L will be equal to 0.15 into 8. In 8 is 120. So you have 1.2 into half. Right? 1.2 into half is going to give you 0.6 Newton per meter. Is that clear? So 0.6 Newton per meter is what is going to. So it's a simple question. And what was the next one I told you? 4.7. So 4.7, what is the question?
Two long and parallel straight wires A and B carrying currents of 8 ampere and 5 ampere in the same direction are separated by a distance of 4 centimeter. Estimate the force on a 10 centimeter section of wire.
Right. Right. Value of mu naught. 4 pi into 10 power minus 7. So how to solve this? So what is the formula for force per unit length? F by L is mu naught I1 I2 divided by 2 pi into distance of separation. Mu naught is how much? 4 pi into 10 power minus 7 into I1 into I2 is 40 divided by 2 pi into what is the distance of separation? 4 into 10 power minus 12. So this will go 10 times, this will go 2 times. So 20 into 10 power minus 5 is the force per unit length, but L should come to the other side. So how much is the length of the wire they ask for? You consider a 10 centimeter of wire from here, then what would be the force experienced by this portion? So you know the force per unit length is 20 into 10 power minus 5 or 2 into 10 power minus 4. Then what will be the value of force? So 20 into 10 power minus 5 into 10 into 10 power minus 2. So 200 into 10 power minus 7, answer will be 2 into 10 power minus 5 Newton. So this is going to be the value of force experienced by this 2 into 10 power minus 5 Newton. So clear with this? Now listen. The next concept that we need to discuss is something called as velocity selector. So what is this velocity selector? Listen, if you have electric field and magnetic field, let's say they are perpendicular to each other. I repeat, you have an electric field and magnetic field perpendicular to each other, and you have y-axis. Okay. If we say the electric field value E vector is equal to E times I cap, and B vector is equal to B times minus B times K cap. Okay, this is the value. Now, if we project a particle, a small correction, if we say the electric field is in this direction, I take this as E J cap. So I repeat it. Electric field is along y direction and magnetic field is along z direction. So they are perpendicular to each other. Now, to this perpendicularity, let's say you are projecting a particle, especially projecting a charged particle. Let's say the velocity v. Okay. In the direction mutually perpendicular to both. Okay. So what are the directions you can choose? You can choose positive x-axis or negative x-axis. So what we will do is we will project the particle along the direction of positive x-axis. Then what will v vector be equal to? It will be v times I cap. Correct? So it is going to be v times I cap. Now comes an important question. What would be the, if it is a positive charge? I repeat, if it is a positive charge, what would be the direction of force experienced by this charge due to the electric field? So what would be the electrostatic force experienced by it? It is going to be Q into E, and this is in which direction? What we put is right. It is going to be in the upward direction. So this is the direction in which it experiences Y. So when you have a charged particle, in whichever direction you try to project it, or you keep it at rest also in the presence of electric field, it always experiences a force in the direction of electric direction. Right? In a similar context, what would be the value of magnetic force experienced by the same charged particle according to Lorentz force? So it is going to be Q into VB sine QVB sine 90. So this is going to be Q into V into V. Accept. Right? No. When you say that the electric force, the electrostatic force experienced by the charged particle is in upward direction. In this scenario, what would be the direction of magnetic force experienced by? In this scenario, it is going to be in the downward direction. So this is the direction of magnetic force, and this is the direction of electrostatic force carried out with this. Right. Now, what I want to happen is, observe, answer this question. So this particle is projected in the perpendicular direction. Suppose if electrostatic field is dominating the magnetic field, electrostatic force is dominating the magnetic force, what would have happened to the charged particle? It would have started moving in the upward direction. Suppose the magnetic force dominated the electrostatic force, it would have started moving in the downward direction. But I don't want either of them to happen. Then what should be the scenario? So from this, can I conclude if electrostatic force is equal to the magnetic force in this scenario in terms of magnitude. Okay, then Q into E will be equal to Q into V into V, where Q and Q will get cancelled, which implies E will be equal to E divided by V, etc. Means if you are able to project the particle perpendicular to both electric and magnetic fields with this magnitude, okay, then the particle starts traveling undeviated. What will happen to it? It starts traveling undeviated. Means it is trying to continue in the path along which it was released. There is a meaning. Okay. And since we are choosing the velocity which is related to the electric field and the magnetic field's magnitude, we call this velocity as the velocity selector. That is the reason why the name of the concept is velocity selector. What velocity are we supposed to select? So that this travels undeviated in the presence of perpendicular electric and magnetic fields. Is that clear? So V is equal to E by V, and this is a very, very, very important concept. So we won't consider that. No, because compared to these two forces, gravitational force is very less. Moreover, the mass of the particle itself is going to be very small. Correct? Right? Is it clear? So V will be equal to E divided by any of this. The last concept for today is what happens if you place a current carrying loop in external magnetic. So we saw these points. Charge projected in external magnetic. Yes, we saw this. Similarly, we saw current carrying conductor in external magnetic. Yes, right? Now, we are going to see what will happen when you place a current carrying loop in magnetic field. This is what we are going to see. So, right now the heading has current carrying loop placed in external magnetic field. Current carrying loop placed in external magnetic field. Okay. So how to solve this? Let's say you have a north pole and a south pole, along which you have placed a current carrying loop like this. Okay. place a current carrying loop in this way. And the current is flowing, let's say, in clockwise direction, obviously, according to the connection that I've given. Right? And if I take this current to be I, okay, if I take this current to be I, now our job is to find what will happen to this current carrying loop. Okay, this is where the differentiating factor comes. First is, you know what happens when a current carrying conductor is placed in external magnetic field? It experiences force. Okay, now if I take this to be the axis, okay, I divide it into two equal parts so that I say this measurement of the conductor is A and this measurement of the conductor is B. So this measurement is A and this measurement is B. Okay. Now, if I label this as first conductor, second conductor, third conductor, and fourth conductor, now I'm going to look at it like I'll break it into four different conductors and observe what will be the force experienced by each part of this loop. Right? So, what is going to be the value of force experienced by the first current carrying conductor? It is I into what is this side guys? It is small b into capital P. Capital P is what? It is the value of magnetic field which is going to be from north pole to south pole. So I into small b into capital P into sine of 90 degrees. Okay. So I small b into capital P sine 90 is accepted. Okay. In which direction is it going to experience the force? So it will be into the plane. Right? So it is going to be into the plane. So can I call it as minus k here by putting a vector on top of it? Now what will be the value of force experienced by the second current carrying conductor? What is the value of force experienced by the second current carrying conductor? It is a 0. What is the value of force experienced by the third current carrying conductor? It is I into small b into capital B into sine 90 degrees. So I b into capital B in the direction of. So what is the direction of current? Sorry, so current is this way, magnetic field is this way. It is in the direction of plus k cap. This I will call it like this. Correct? Now what about F4? This again is 0. Why? Because the current and the magnetic field are in opposite directions. Okay. If you observe, this force is in the direction of minus k cap. The third force is in the direction of plus k cap. They are opposite conductors, and the force is also in opposite direction. If you see the net force experienced by this system, if I put a question on what is the net force experienced by the system, what will the answer be? What is the net force experienced by the system? It is F1 vector plus F2 vector plus F3 vector plus F4 vector, and the answer is going to come out to be the 0. And answer will come out to be a 0. Right? Now the next question is, the answer here is 0 when net force is going to be 0 in this. What will happen to higher rating study? So there is a possibility of torque to act. So why is it happening? Because one force is into the plane and the other force is out of the plane. So these two forces, with the help of these two branches, will put the whole coil in a circular coil. Are you able to understand? So this will go into the plane, this will come out of the plane. So when you see from top, what will it appear as? When you see it from the top, it will appear as if it is revolving in the anti-clockwise. Clockwise or sorry, clockwise. Yeah. So it will appear as if it is revolving in the clockwise direction. Is that clear? Right. So what is going to be the torque experienced by it? Can I rub this part? First copy it. Here. So when I rub this, now see, if I try to calculate the torque experienced by the first current carrying conductor. So
Sir?
torque experienced by the first current carrying conductor. What is it going to be? Torque is equal to force into perpendicular distance. So what is the force? So in which direction will the force act? So force is into the plane and perpendicular distance is this much. So how much is the perpendicular distance from the axis of rotation? A by 2. Because this length is A, axis will be exactly at the center. This distance is A by 2. So torque acting on the first particle is going to be forces I into small b into capital B into the distance is A by 2. But what is going to be the direction of this torque? What is going to be the direction of this torque? How did you know that? When you see from the top, it is revolving clockwise. So clockwise means curl your fingers in the clockwise direction and extend your thumb. This is the direction of minus j cap. Accepted. I told you already that clockwise moments are negative. Okay. Similarly, what is going to be the torque experienced by the second particle? Obviously, 0. Similar is going to be the torque experienced by the fourth conductor. So what is going to be the value of the torque experienced by the third conductor? Same force into perpendicular distance. So what is the value of force? IB into capital B into the distance is how much? Same A by 2, but what is going to be the direction in this scenario? It's going to be in this way. It is plus J cap. Sorry. Think about it. It still be minus J cap. See, force is in this direction. This is the distance. Okay. But if you see from the top, it is still revolving in clockwise direction. So what is the direction of net torque? Curl your fingers in the clockwise direction from the top and extend your thumb. It is in the downward direction. So it is still minus J cap. So put a bar on top of this and top of this. Okay. Now what will be the net torque acting on the particle or the system? You need torque 1 vector plus torque 3 vector, and how much is going to be the magnitude? IB into capital B into A by 2 plus A by 2 will give me an A in the direction of minus J. Okay. So what is this B into A called as? Area of this conductor. So it is going to be IAB in the direction of minus J cap. So this is going to be the net torque experienced by this loop. Okay. So the net torque experienced by this loop is going to be I into capital A into capital. Same.
So how will you find A and B? It will be the
Pi r square. It will be the area of that particular sheet. I have something important to tell you. Okay. So first I wanted to stop with mathematical equations. Then I need to relate this concept to something else. from your electrostatics. Okay. So first you master this mathematical expression. The next class maybe I'll explain you what is the time? 5:57. Next class I'll explain you how to analyze this equation and how to relate it to electrostatics. So apart from that, any other doubt? So this is about the torque experienced by a current carrying conductor. So you wrote the heading, right? Current carrying coil placed current carrying loop placed an external magnetic field. You can write it in the bracket, it will experience torque. So there are two important points I want you to remember. One is when you talk about an isolated conductor experiences force. Whereas a current carrying loop or a current carrying coil, whichever is closed, placed in external magnetic field will experience torque. Okay, so torque will create a rotational effect, force will create a translatory effect. Okay, so that's it. So apart from that, any other doubt? Is everything clear?
Sir,
Okay. So those who are online, any doubt raised?
sir, how is torque is anti-clockwise, sir?
Sorry?
Sir, how is torque 1 is minus j cap, sir? I didn't get it. The direction.
Because the coil is revolving in clockwise direction. Did you understand that? Did you understand that the coil is revolving in clockwise direction? Because one force is into the plane, the other force is out of the plane. So it starts revolving like this. So when you see from the top, the current revolves in the clockwise direction, accepted?
Yes, sir.
Okay. When when the coil is revolving in clockwise direction, curl the fingers of your right hand in the clockwise direction and extend your thumb.
Okay, sir.
Okay. So clockwise moments are always negative. That is the reason why it happens. Okay. Is it clear?
Yes, sir.
Yes, sir.
Okay. So any other doubt?
No, sir. No, sir.
Then we'll wind up.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir.